Today we will be looking at more sampling distributions, specifically what sample means. Remember, proportions, they summarize categorical variables. Means summarize quantitative variables. Not only can we use all the same concepts, but almost the exact same model. Okay, so this mu is obviously the mean. This sigma over the square root of n is our sample standard deviation. Okay, so slightly different terminology for the formulas, but once we find the sample mean and sample standard deviation, everything else is exactly the same as it was last semester. The sampling size of any means becomes more nearly normal as the sample size grows. And this was demonstrated in our DICE activity and our random table activity, that as our sample size increased, our distribution or histogram or a dot plot became more and more fairly symmetric. All we need is for the observations to be independent of each other. So the rolling each die is independent, the random numbers are independent and collected with randomization. We don't even care about the shape of the population distribution. This is the fundamental theorem of statistics called the central limit theorem, or the CLT. Just like with proportions, we have three assumptions and conditions. The first one is the same, randomization. The sample should be an SRS of the sample of the population, or at least representative of the population. The 10% condition, just like with proportions, the sample size n must be no larger than 10% of the population. Just like with binomial models, remember to assume independence and you are pulling without replacement, you have to have the sample be less than 10% of the population. The last but not least, the large enough replaces the success-fail condition for proportions. The CLT doesn't tell us how large a sample we need. For now, you need to think about your sample size in context of what you know about the population. Typically, if n is at least 30, we assume normality. Okay, if the sample is less than 30, what you have to do is you either have to make a box plot or a histogram or a dot plot to determine if there's any skewness within the sample. The CLT says that the sampling distribution of any mean or proportion is approximately normal. Okay, so the central limit theorem says that any mean or proportion is approximately normal. But which normal model? Question. Well, for proportions, the sampling distribution is centered around the population proportion, and for means, it's centered at the population mean. Okay, so notice for our proportion, the mean is P, population proportion. The standard deviation, remember, is the square root of P times 1 minus P or Q all over N. Now, if we look at the sample mean, it's the same thing as the population mean. And the standard deviation, we take the population standard deviation over the square root of the sample. Well, what can go wrong? First, but don't confuse the sampling distribution with the distribution of the sample. When you take a sample, you look at the distribution of the values, usually with a histogram. Okay? And you may calculate summary statistics, meaning you might find the mean and the standard deviation of that sample. The sampling distribution is an imaginary collection of the values that a statistic might have taken on for all random samples, the one you got and the ones you did not get. For example, our group, our DICE activity, the ones we got are definitely there, but remember there's a whole bunch of other scenarios that we did not get. Beware of observations that are not independent. Remember, the central limit theorem depends crucially on the assumption of independence. You can't check this with your data. you have to think about how the data were gathered. In our dice activity, each dice is independent of each other because we assume they are all fair. So each roll is independent of each other. In the table of random digits example that we looked at, people were assigned a number line randomly, and then we went from there. Okay. Watch out for small samples from skewed populations. Remember, the more skewed the distribution, the larger the sample size is necessary for the CLT to work. Okay. All we have left now are examples. So, a college physical education department asked a random sample of 200 female students to self-report their heights and weights, but the percentage of students with body mass indexes over 25 seems suspiciously low. One possible explanation may be that the respondents, quote, shaded, unquote, their weights down a bit. The CDC reports that the mean weight of 18-year-old women is 143.74 pounds with a standard deviation of 51.54 pounds. But these 200 randomly selected women reported a mean weight of only 140 pounds. Based on the central limit theorem and the 68, 95, 99.7 rule, does the mean weight in this sample seem exceptionally low, or might this just be random sample-to-sample variation? Okay, just like we did with proportions, we're going to set this up with 4 steps. But before we do any of that, I get into a huge habit of underlining key components. Okay, this is the same example we looked at yesterday. We're just talking about means instead of percentages or proportions. So let's take a look. It says we have a random sample of 200 female students. Let's see. We also have the CDC reports that the mean weight is 143.74 with the standard deviation. But these 200 randomly selected women report only a mean of 140. Okay, notice we're going to use the CLT and the 68, 99, 95, 99.7 rule. Does this mean that the sample seems exceptionally low, or might this just be random sample-to-sample variation? First step is our state step. For the state step, we're going to say mu is the true mean weight of 18-year-old females. Now, once we get to the plan step, remember the first one? We have to state that there is randomness, and we know there's randomness because, oh, that's weird. If we look back up at the problem, it says a random sample of 200 female students. So what I like to do is I just like to state exactly what it said in the context, okay? The 10% condition, just like with proportions, 200 has to be less than 10% of all 18-year-old women on this campus. And then last but not least, large enough. For the large enough, because the sample size is larger than 30, right? 200 is definitely larger than 30. We can assume that the distribution of college women's heights is approximately normal by the central limit theorem. What's left for us to do is the do step. So the first step in our do step is to figure out what our sample mean and standard deviation is. Remember, the sample mean is going to be the same thing as the population mean, which was given to us of 143.74 pounds. The standard deviation, I have to take our population standard deviation and divide by the square root of 200, and we get approximately 3.644 pounds. Now, because this question said specifically to use the 68, 95, 99.7 rule, what we will do next is we will actually draw the picture there. And if we need to talk about the picture, we can definitely do that. I'm having some issues. Okay, so we can zoom in on our 68, 95, 99.7 rule. Remember, the mean goes in the middle, and then I add the standard deviation from the previous step. And so this is what we're looking at. Now, because it says they thought 140 was less than the population mean, is this unusual? Are they underrepresenting their weights? Okay, so here's our conclude step. So the 68, 95, 99.7 rule suggests the reported mean weight of 140 pounds is lower than expected, so it does not seem unusual. And the reason why it doesn't seem unusual is because 140 pounds falls somewhere in about here. And we know definitely 16% have that weight or less. So 140 pounds really isn't significant. Last example. This time, suppose the number of texts sent during a typical school day by the population of students at a large high school follows a right-skewed distribution with a mean of 45 and standard deviation of 35. How likely is it that a random sample of 100 students will average at least 50 texts per day? Okay, so this one is slightly different. Again, I'm going to start off by underlining key information. We know that we have a right-skewed distribution. We have a mean of 45 and standard deviation of 35. We have a random sample of 100 students. We want at least 50 texts per day, and we have that clue average, which tells us we're referring to means. So we're just going to follow our same 4 steps. First step, the state step. Remember, our first step is the state step. So here we're going to say mu is the true mean number of texts sent per day. Remember the second step. The second step is the plan step. Your first step is to state that it is a random sample, and I usually pull that verbatim from the text. So note, it says a random sample of 100 students, so we write a random sample of 100 students next to random. After random, remember we have the 10% clause. Because we are choosing students without replacement, we have to double check and make sure that 100 is less than 10% of the students at a large school. Okay, even if we were at Bellevue East, 100 students would still be less than 10% of our population. So we're good. And then remember, the third one is the large enough. Because our sample is greater than 30, right, 100 is larger than 30, we can assume the distribution of text is approximately normal by the central limit theorem. That is step 2. Step 3 is the do step. And the first thing that we need to do in the do step is to identify the sample mean and standard deviation. Okay, so our sample mean is 45 texts. It is the same thing as the population mean. And the sample mean, standard deviation, we take the population standard deviation divided by the square root of the sample. So we have a mean for our sample of 45 text and a mean for our standard deviation of our sample to be 3.5 text. Then we're going to find a z-score, just like we did with normal distribution curves last semester. So note, we have the probability of x bar is at least 50 is equal to the probability of z is greater than or equal to 50, because we want to know what's the average is going to be at least 50 per day, minus the mean 45 divided by the standard deviation 3.5. We do get a z-score of 1.43. Remember, you can either go to normal CDF or you can draw a normal curve and use your chart, subtract it from 1 and shade to the right. Don't forget to write n parentheses 45 comma 3.5 to ensure you receive that essentially correct. And then all that's left for us to do is our conclude statement. And I typically will pull the exact same thing from the actual question itself, verbatim. So we have this is our question. So according to the model, the probability that a random sample of 100 students will average at least 50 texts per day is about 7.66%. Notice we used a huge chunk of that question. I would just rephrase the question. And that's all you need to know for sample means. Now you're ready for some more practice. Hooray, done with Unit 6 notes.